In this session we will see the anatomy of Mapreduce. Till now we saw the storage part of Hadoop, that is HDFS. We saw how data is divided into blocks and stored in the cluster. Now this data has to be processed to get some meaningful result from it. This is where Mapreduce come into picture. Mapreduce is a framework used to process the data stored in HDFS cluster. In this session, we will learn about Mapreduce framework and how data is processed using this framework. Java is the native programming language used in Mapreduce. It also supports other programming languages like C++, Python, Perl, Ruby, etc. Let us see some components of Mapreduce. Like HDFS has name node, Mapreduce has job tracker. In HDFS, name node manages how data is stored in the cluster. In Mapreduce, job tracker manages how this data is processed in the cluster. It coordinates all the jobs in the cluster. It also keeps track of the overall progress of each job in the cluster. Like HDFS has data nodes, Mapreduce has task trackers. In HDFS, actual data is stored in data nodes. In Mapreduce, task tracker runs the task that does actual processing of this data. Also, it sends the progress reports to the job tracker at regular interval. Now we shall see the working of Mapreduce. Before we start, let me confirm that in this session we will be learning Mapreduce version 1. There will be a separate session on Mapreduce version 2, which is also called as Yarn. Let us not worry about it now. So how does this Mapreduce work? Mapreduce works on the principle of divide and process. It means processing of data is divided into tasks, and these tasks are run across the cluster. Consider a Mapreduce program. This program takes log.txt file as input, and then it processes the data in this file, and finally it produces some output. So for any Mapreduce program, you need to specify input path and output path. I have also specified job client here. So what is this job client? If you recall HDFS sessions, you will see that there we had defined HDFS client. Similarly, Mapreduce has job client. Job client is the one that interacts with job tracker, just like HDFS client interacts with name node. We are hearing a lot of job keyword here, like job tracker, job client, and job tracker manages all the jobs in the cluster. So first we need to know what a job is. In Mapreduce, basic unit of work is called a job. So when you write a Mapreduce program, that program is converted into Java objects called jobs. These jobs are divided into tasks and then they are run across the cluster. That was all about jobs in Mapreduce. Let us get back to the Mapreduce program. Now we shall run the Mapreduce program. As soon as you run it, a job submitter instance is created. This instance will ask the job tracker for a new job ID by calling getNewJobID function on the job tracker. This function call will return a new job ID. Let us say the job ID is job_1234. Job ID is used to uniquely identify a job in a cluster. Every job should be associated with a job ID in the cluster. A directory by the same name is also created in the cluster. Next, the job submitter will check whether the specified output directory already exists in the cluster. If at all the output directory already exists, then the job is not submitted and an error is raised. In our cluster, this directory does not exist. Hence, there is no error. Now the job submitter will compute the input split. If it cannot compute the input split, then again an error is raised and the job is not submitted. Let's say there are no errors at all and input split is computed successfully. So what is this input split? Let us not go into more details now. For now, let us just say that the input data is divided into smaller chunks, and a reference to these chunks is called input split. If you recall the HDFS sessions, you will see that log.txt file is divided into blocks and stored on the cluster. So input split is an array list that contains references to these blocks. By default, one split will refer to one block. This is just the default behavior. You can always change the default behavior. You can write your own program such that one split refers to multiple blocks. After computing the input split, all the resources required to run the job is copied to the cluster. In fact, it is copied to the newly created job ID directory. Here the resources copied are input split computed by the job submitter, jar file of the Mapreduce program. Obviously, you cannot run the program on the cluster without the jar file. Hence, the jar file is copied. Also, the config file is copied. After copying the resources, job submitter tells the job tracker that the job is ready for execution. It says so by calling submit job function on the job tracker. After submitting the job submitter will be waiting for the progress status of the job. Every second, the job tracker will notify the progress status of the job to the job submitter. This is how a job is submitted to the cluster. After the job tracker is indicated that the job is ready for execution, job tracker will put it into an internal queue. Then the job scheduler will pick it and initialize it. Let us see how a job is initialized. As a part of initialization, tasks are created here. In order to create tasks, job scheduler first retrieves the input split. For each split, a map task is created. Our job has 3 splits, so 3 map tasks are created here. This is how processing of data is divided into tasks. Instead of a single task processing the whole data, multiple tasks are created to process the data across the cluster. This is a huge performance gain, and it is the core of Hadoop. Now we need to create reduce tasks. Number of reduce tasks is specified in the Mapreduce program. Function to set number of reduce tasks is setNum reduce tasks. Let's assume that we had set number of reduce tasks to 2 in our Mapreduce program. Hence 2 reduce tasks are created. Along with map tasks and reduce tasks, 2 more tasks are created. Job setup task and job cleanup task. All these tasks are wrapped in the job object. This is how a job is initialized. Now all these tasks has to be assigned to the task trackers so that they can process the data stored across the cluster. Let us see how tasks are assigned and which task is assigned to which task tracker. Task trackers periodically send heartbeats to the job tracker. Through these heartbeats, the job tracker will come to know which task tracker is up and running. Heartbeats also say whether a task tracker has enough resources to execute a task or it does not have resources to execute a task. If enough resources are available, then the tasks are assigned to those task trackers. Here resources are nothing but CPU, cores, RAM, etc. Let us assume that all the data nodes in the cluster have enough resources to execute a task. Job setup task is run first. It is run before any other map task is run. Job cleanup task is run last. Let us assume that job setup task is assigned to the task tracker running on data node 1 and job cleanup task is assigned to the task tracker running on data node 5. Now task tracker on data node 1 runs the job setup task. The responsibility of this task is to create the final output directory that we have specified in our Mapreduce program. It also creates a temporary working space for this job. After the job setup task is complete, map tasks are assigned to the task trackers. Map tasks are assigned such that its input split is as close as possible. In our cluster, first split of the file is in the data node 1. So the first map task is assigned to the task tracker running on data node 1. Similarly, second map task is assigned to the task tracker running on data node 2. And once again, third map task is assigned to the task tracker running on data node 1. That's because third split is available in the same data node. The concept of assigning the task where data already exists is called data locality optimization. Along with resource availability, data locality is also considered while assigning a map task to the task tracker. For the reduced tasks, data locality optimization does not hold good. So wherever a slot is available to run the task, reduced tasks are assigned there. Let us assume that reduced tasks are assigned to the task trackers running on data node 5 and data node 6. This is how task assignment is done in Mapreduce. Now we shall see how these tasks are executed by the task trackers. First, the jar file is copied to the data nodes on which the tasks are running. Earlier we had copied the jar file to the HDFS cluster. From there it has to be copied to the local file system. In fact, it has to be copied to the local working directory of the data nodes where the tasks are running. And then the contents of this jar file are extracted to this local working directory. After this, the task tracker will create an instance of the task runner. The task runner instance will launch a new JVM to run each map task. A separate task runner instance is created because any bugs in the Mapreduce program should not bring down the task tracker. In our cluster, 2 map tasks are running on data node 1 and 1 map task is running on data node 2. All these tasks are running in parallel. That's because there are enough resources available in our cluster to run these tasks in parallel. Each of the map tasks will process the input split assigned to them. After processing the input split, map outputs are returned to the local file system. That is, the local file system of the data nodes where the map tasks are running. It is an important point to remember. Map output is not returned to HDFS cluster. Rather, it is returned to the local file system. Suppose enough resources are not available in the cluster to run all the 3 map tasks in parallel, then the tasks are run sequentially. All the task trackers periodically send status update of each task to the job tracker. The job tracker will combine the status update from all the task trackers and then it will send the job progress status to the job submitter. After 5% of the work is done by the map task, reduce tasks are started. This is configurable. You can start the reduce task early or you can delay the start of the reduce task. We can start the reduce task after 10% of the work is done, or you can start after 20% of the work is done, or 75% of the work is done, or whenever you want. There are pros and cons for early start and late start of the reduce task. Responsibility of the reduce task is to process the map output and produce the final output. So the reduce task will start copying the output from the map task. How does the reduce task know on which data node map outputs are available? A thread in the reduce task will periodically check with the job tracker to get the location of the map output. Since the job tracker itself assigned the map task, it knows on which data node map outputs are available. As a result, job tracker will notify the location of map output to the reduce task. In this way, the reduce task knows on which data node map outputs are available. Reduce task will start copying the map output. Finally, after copying all the map output, reduce task will start processing it. After processing, output is returned to the HDFS. This is the final output and we want it to be reliable, hence it is stored in HDFS. After all the reduce tasks are complete, job cleanup task is run. This task will move temporary working directory to final working directory because all the processed output is in the temporary working directory and then the temporary working directory is deleted. If the job succeeds, an empty file by the name _success will be created in the final output directory. And if the job fails or gets killed, this empty file is not created. So a job is declared succeeded or failed only after the job cleanup task has completed. Once the job tracker knows whether the job is succeeded or failed, it will notify the same to the job submitter. In this way, finally the user knows whether the job succeeded or failed. That was all about how Mapreduce works. Let us summarize the contents of this session. Job submitter computes the input split and then submits the job. Job scheduler initializes the job object. It creates the map tasks, reduce tasks, job setup task and job cleanup task. For each input split, one map task will be created. Number of reduce tasks is configured in the Mapreduce program. Job tracker will assign these tasks to the task trackers based on resource availability and data locality optimization. Task tracker will run these tasks on separate JVM. First the job setup task is run, then all the map tasks are run, and then the reduce tasks are run, and finally job cleanup task is run. Map output is returned to the local file system and reduce output is stored in the HDFS. That was all about how Mapreduce works. Thank you for listening to this session.